Ready? Oh, fine. Okay. Let me just turn this down. Good afternoon. Let me introduce myself. My name is Guinn. I teach physics here on the Clarkston campus. The title of my talk today is The Music of the Spheres, the Physics of Music, and the Music of Physics. What I'd like to do is try and give us a little introduction about the physics of making music, making sound, and how that relates to music. But then also what I'd like to do is try to give us a bit of an appreciation of just how universal or pervasive music is, if we could really just expand our understanding of what we usually think of as physics. Sorry, as music. Sorry. What we've just been listening to as you were coming in and taking a seat was, oops, let me put that back on. The recording of the Harmony of the World. This is a realization for the ear of Johannes Kepler's astronomical data from Harmonices Mundi from the year 1619. There's a case there if you'd like to take a look at it later on. Johannes Kepler was an astronomer from the 16th and 17th centuries, and he was very, very interested in the orbits of the planets, in particular trying to understand why the planets had the particular orbits that they did. Now, this was prior to Isaac Newton's law of gravity, and so he did not have the laws of mechanics to try and explain what was causing the planets to move the way that they did. What he did was to take the planets and put them on spherical shells, and then nest these shells in between these geometrical figures, the Platonic solids. He didn't have an explanation for this. It was actually the other way around. He had the radii of the orbits, the size of the orbits, and he noticed that they happened to fit very, very well in this sort of construction. Actually, he was able to fit the radii to within a few percent, which was a pretty surprising idea. Now, along with the structure of the cosmos that he had, he also believed that the planets had tones or music associated with them. The faster the planet moved, the higher the frequency or the higher the pitch of the tone. The slower the planet moved, the lower the frequency or lower the pitch. The planets that were the sun closest to the sun moved the fastest and would therefore have the highest frequency or highest pitch. The planets that are farthest from the sun move the slowest and would therefore have the lowest frequency or lowest pitch. I won't say pitch for all of them because it will turn out that when we get far enough away, according to the realization we were just listening to anyway, the sounds are really not pitches anymore. They're more like pulsations or almost like a drum beat to a certain extent. What I'd like to do is to start this over again so that we can kind of get an idea of what we're actually listening to. Oops, sorry, hold on. Let me turn this back up. I just got over. So this is the planet Mercury. Now Mercury has a relatively elliptical orbit, and so it's varies in distance from the sun, and so its pitch actually changes in its orbit. So for even a single planet that gets closer and farther from the sun, it will go faster and slower, and the pitch will change. This is Venus, the next planet. The more circular orbit, and so its frequency doesn't change as much. And then the Earth. So going out from the sun, Mercury being the Earth. Now, the Earth has a somewhat elliptical orbit, and its frequency is going to change over time. You might be able to hear it if you listen long enough. It actually started out higher and is going down, and then it'll go back up. Okay, and then there's Mars, and et cetera, et cetera. Now, I'm going to stop there because I want to come back to Kepler, this sound created by the Earth had about a half of a tone difference from its highest frequency to its lowest frequency. A half a tone on a major scale, Kepler associated with the two notes mi and fa. He thought that this really had significant importance, so much so that he associated mi with misery and fa with famine. And he believed that it was because of these tones or music given off by the Earth that humans had such a hard lifestyle back in the 16th and 17th centuries anyway. He believed that humans were connected to these sounds from the planet through our souls, that our souls were connected to this cosmic harmony. And in this case, the entire cosmos was filled with music, and in the case of people living on the Earth, it was really to our detriment as opposed to any benefit for us. Typically, we usually think of music as a collection of pleasant sounds rather than detrimental sounds. What I'd like to do is talk a few minutes about what causes sound, how sound is made, and then later on we'll see how it's related to music. Now, let's imagine we've got some oscillating object, something that's vibrating. This can be maybe either a string on a violin, so we have a vibrating string. This could be perhaps a speaker on a diaphragm on a speaker. It could be your vocal cords vibrating. It could be my hand just moving back and forth. So let's imagine that we've got some object that's vibrating in space. Now, let's say my hand, for example. When my hand moves forward, it compresses the air in front of it. That then pushes on the air in front of that, which pushes on the air in front of that, which pushes on the air in front of that, et cetera, et cetera. Then when my hand moves backwards, it leaves kind of a little empty space slightly in front of it. Well, that kind of draws in the air in front of it, which draws in the air in front of it, which et cetera, et cetera. Now, as my hand goes forward and back and forward and back, it creates these vibrations, these high-density regions and low-density regions, which then propagate through space and go into your ears. Now, if I could actually do this fast enough, we would perceive it as a sound. So I can't move my hand that fast, but I have a speaker here that we can move that fast. So I'm going to start moving the diaphragm of the speaker. So this is just a speaker diaphragm in here. And you'll notice this thing is going in and out once a second. Well, it's creating a sound wave with a frequency of 1 cycle per second. But it's too low for us to hear. So I'm going to speed this up. I'm going to increase the frequency. So you'll notice it's going faster. Everyone see that?
Show that to the camera? Well, oh, that's why something in the etching.
How's that?
Do it a little closer. And don't move so fast because can you move it up to the left a little bit? Here you go. Do something up. Okay. Something like that. Okay.
Are we going to have a commercial break? All right. So let me speed this up a little more. Okay, so you can see it's just going faster. So eventually it's going fast enough that we actually perceive it as a sound wave. Now this is at, let's turn this down slightly, that's 100 cycles per second, or 100 hertz. We can turn this up more. There we go. Now that's 1,000 cycles per second, 1,000 hertz. And we can go up higher than that. Now, our ears can hear sounds from frequencies of about 20 hertz to about 20,000 hertz. But we don't really perceive pitches or difference in pitches from around 40 to 4,000. So we can actually hear things quite a bit more than we can actually perceive them as, say, musical pitches or something like that. Now, to see how these sounds are made in a more physical sense, let's go back to this idea of a string on a violin. We've got basically a one-dimensional object. If we can kind of ignore the thickness of the string, we've got the string held at one end and held at the other end, and somehow it's vibrating. What I'd like to do is take a look at the way this one-dimensional, or basically one-dimensional object is vibrating. Now, the string on a violin is very, very tight, so it's a little bit hard to see details on how that thing is moving. So I'm going to look at something a lot bigger and not quite so stretched with such a high tension. So I'm going to use this slinky here. Fred, is your right there in the corner? So it looks funny. So we can kind of imagine the string like this slinky, although the slinky is sagging quite a bit more than the string is. Now, if I move my hand back and forth very quickly, you'll notice that I create a wave or a pulse that travels back and forth down the slinky. Everyone see that? Okay, this is kind of like a sound wave. If I were to move my hand or the speaker very quickly, it makes this pulse of sound that would travel outward. All right, everyone see that? Now, what I want to do is I want to look at something else, and I immediately have to change from this because this is a little bit too loose. Wait, Fred, don't go anywhere. Okay, now I need something kind of in between the violin string and the slinky. So I've got this chain here. Now, again, I can send kind of a pulse down the chain. Can you see that? Moving back and forth. Now, if I were to move the end of this chain kind of in a random way, I basically just kind of end up with a random motion in the chain, kind of like static. However, if I move my hand in a very regular fashion at a particular frequency, we end up with a very different kind of wave. We end up with something that doesn't look like it's moving back and forth. It's basically staying stationary on the chain. This is called a standing wave. This particular way that the chain is moving is called the fundamental mode of oscillation, or the fundamental normal mode. Now, I'd like to point out just a couple aspects about this. First, notice that although my hand is moving a little bit, my hand and Fred's hand are basically stationary. We'll call these the nodes of the oscillation. The middle of the chain is moving the most. We'll call that an antinode. So we've got two nodes and one antinode. Okay? There's another frequency, a higher frequency, where we again get a standing wave. Now in this case, again, my end and Fred's end are both nodes, but there's now a node in the middle. We'll call these node points. Well, how many antinodes do we have? We have two antinodes. The two that are in between the nodes, that's where the chain is moving the most. And we could go to a higher frequency. Where now we see we've got 4 nodes and 3 antinodes. Everyone see those? Okay. And shall we go for one more? See if we can do it. It's actually not so easy to tell you. Okay. All right, there we go. Okay, there. So, what was it, Fred? Okay, there we go. So we got 5 antinodes and 5 nodes, 4 antinodes. Everyone see that? Okay. All right, one more. Should we try Fred? One more. All right, let's make it a little bit longer. All right, ready? All right, here we go. There we go. Okay. All right, very good. Now, Excellent. Thank you. That takes my foot off. Okay. I'd like to just sketch what these look like, because I'm going to come back to that. The first mode looks like that. The next one, you might say, looks like that. The next one, like that. The next one, something like that. Okay? You would take a snapshot of the change at one particular instant. I would like to sketch these in a slightly different form. I want to draw what the amplitude of the motion looks like. In other words, we've got a node here, an antinode here, an antinode here. I'm going to draw the first one basically the same way, but I'm going to draw the second one like that to indicate the two antinodes, but to indicate that when one is up, the other is down, I'm going to indicate this as, say, positive and the other is negative. And we'll just think that this one is, the whole thing is positive. The next one will look like that, where the two ones on the outside have the same phase. In other words, they're both up, while the one in the middle is always opposite or underneath or different from the other two. And then the next one looks something like this. Okay, everyone get the idea? So basically, we're looking at these one-dimensional modes, and we're looking at the amplitude in terms of where is the change relative to other parts. Say, this is always up, the whole thing is up, but when this is up, this is down. When this is up, this is down, this is up. When this is up, this is down, this is up, down. Does that make sense? Okay. These different modes are called the harmonics, or the overtones of the oscillating object. Now, these are very, very important, because when a musical instrument is played, like the violin, say if you bow or pluck a string, it oscillates in its fundamental mode, but it also oscillates with a certain amount of the higher overtones at the same time. And it's the amount of these different overtones that makes one instrument sound different from another instrument. So you can play a middle C on one instrument and a middle C on another instrument, and they would sound completely different. And it's because the different instruments, although they have the same fundamental frequency, they have different amounts of these other frequencies that give a particular instrument its color or makes one instrument sound different than another one. This also helps us understand why instruments are sometimes played in different places, for example. With the violin, sometimes an instrument is bowed, say, up here, but down here, we get a very different sound. So the same string can give rise to different tones, different sound colors, just by playing it in different places. With the harp, if the harp is played down near the soundboard, the string sound is a much more twangy sort of sound. That's called playing it presso la cava, or near the table or near the soundboard. Another type of one-dimensional system that operates like this, so we were looking at basically a string, another one-dimensional system would be, say, a column of air. Air can also vibrate in different kinds of normal modes. For example, this is a toy called a whirly, which is basically just an open tube that has air in it. If I twirl this around, the air is forced through, and the ridges on it cause the column of air to vibrate. The faster the air goes through, in other words, the faster I rotate it, different frequencies occur. But just like the chain, we don't get a continuum of frequencies. The modes don't go smoothly from one frequency to another, but they jump from one frequency to another. And we can hear that very, very easily. So the sound jumps when you go from one mode to the next. Now, this is exactly the way sounds are created in simple single column tube instruments. For example, a bugle or a natural trumpet. A natural trumpet is a trumpet without the keys, so you cannot change the length of the trumpet. Those instruments are basically just a length of tube. And the way that the air in the tube is vibrated is by sending the air through with your lips and vibrating your lips. Like that. Now the difference between this and a bugle is two things. Well, two major things. One is that a bugle or a natural trumpet will have a bell at the end, which helps the sound disperse from the end. Okay, and the other difference.
Can you hold that to the camera?
Yes.
A precision player?
What? No. There, see?
I like to get into it.
Okay. The other thing is a better way of getting the vibrations into the tube, which is what a mouthpiece is for. So, other than that, so obviously, yes, a bugle has a much better shape, and the fact that it's made out of brass helps the tone of the sound. But the basic construction is exactly this. And because a bugle is only a fixed length of tube, it can only play certain frequencies, and that's why bugle tunes have the particular sound that they do. You can only play this certain interval of sound, and so you can have tunes like reveille, ba 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 ba, because you can't play anything in between. So. Right again. Well, the fact is, those are basically the same tones as we have in orally. So, it's the same tones that we get in orally because they're fixed by the length of the tube. Now, those so far have all been one-dimensional oscillators, you might say. The string, the column of air. What about something that's two-dimensional? For example, a drum head. Let's imagine we have a square drum head. Now, I can't demonstrate this so well, but I can show you what they would look like. So, here is a square drum head. The lowest mode, the fundamental mode of oscillation, would look something like this. So the whole thing coming up, the whole thing going down. Okay, like that. But, whoops, I don't know why I stopped. But now, because it's two-dimensional, we have different ways of getting higher modes. So here would be one of the overtones, where we have one half going up, the other half going down, and like this. But now, let me point out here, we know along the edge there's no motion, so those are like the nodes of the one-dimensional oscillators. We'll call these nodal lines. However, you might also notice this line right through the middle here, that one is not moving at all. Anyone see that? That line is not moving, so we've got a nodal line right through the middle of the drum head. Another mode would look something like this. where we've got two corners coming up and the opposite corners going down. And notice in this case, along the external side being a nodal line, we now have two nodal lines running through the middle. One through here and one through here, breaking the box, break the square into four equal-sized squares. Well, if we go back to our trick that we did here to look at the amplitude, we can look at the amplitude of this motion like this. So here is the square wave mode, where we've got the whole square going up and down, one half going up and down this way, one half up and down this way. Then we can divide it into 4, we can divide it into 3, we can divide it into 6. So there are all sorts of different modes that we can get for these two-dimensional square modes. The violin doesn't have to be a square. You can have a circular one. We actually have a circular one here. If Fred can just hold this for a second with me. This is actually very difficult to get any of the high modes on it, but we can show you the lowest mode anyway. Basically, where the whole thing is just going up and down like that. We try getting some of the other modes, but the side starts oscillating a whole lot more than the fabric does. So let me just show you things. Let's get right to the amplitude, because we start getting something very, very interesting when we look at the round amplitude. Not only can we start breaking it down left, right, up and down, but we start getting some different oscillations from the middle versus the outside. So in this case, we would have something where the middle is going up, the outside is going down, and these are then the nodal lines here. Okay, we start getting some much more complicated behavior. Now, when I said that we were looking at the vibrations of the string for a violin, I mentioned that the strings of the violin is a one-dimensional object. However, these two-dimensional modes are extremely important for violins also. It was discovered that when violins were played, the string was not the only thing that was oscillating. The air inside the violin was oscillating, and the top and the bottom plate, the belly and the back of the violin, were also oscillating. Well, this was very, very important for violin makers as well as people interested in the reconstruction of damaged older violins, and in particular, this is a local luthier, violin maker, and repair person by the name of Paulo Alfaro. He works for, he is Alfaro Violin. And here he is looking at a violin plate. This violin plate, actually. And he is testing it in one of two ways. It's not clear exactly how the old violin masters made and tested their violins, but it is thought that they probably used both of these methods. Here, he is checking a tap tone, and here he is checking the rigidity of the plate, and I'll get back to that in a second. Just like we can look at the nodal lines of the square and the round drum head, if you take a violin plate and put it over an oscillator, you can look at the nodal lines of different modes of oscillation for a violin plate. It turns out that 3 of them that are particularly important are numbered 1, 2, and 5 in terms of increasing frequency. These lines, or these areas here, show the nodal lines or nodal regions for the violin plate. So this mode here is one where the violin is kind of going like this, with the opposite corners going up and down. This one is going like this, and this one is going like this. Now, what the tap tones tell us is, if you hold the plate along a nodal line, so let's say I hold it in the middle here, and tap it at one of the regions that's oscillating, so just listen here. Okay, and now I'll hold it, say, along one of these nodal lines, and tap it in the middle. Can you get a difference? And then if we hold it, say, here, Okay, so there's a definite difference in the tap tone. That's what these are called, the tap tone. And it is thought that by listening to these tap tones, the masters would then take more wood off of the plate to tune the plate to get just the right relationship between these modes. What Mr. Alfaro was doing on the next slide, on the previous slide, or the next image, was holding the plate and actually trying to move it back and forth like this to test the rigidity. So moving it like this would test the strength of this mode. This one would test this one, while this one you'd have to push on it in the center to test the strength of the plate for that mode. So these oscillating modes are extremely important in terms of things like making and repairing violins. Now, if we can imagine taking a two-dimensional object like this round drum head, and let's imagine wrapping it around into a sphere. So we might imagine we had like a large beach ball or a balloon or something like that maybe holds its shape because of the rigidity of the drum head, or maybe just because there's enough air inside to hold it. We can imagine some two-dimensional oscillating modes for a spherical drum head. Well, what would these look like? Let's see. Okay. The lowest mode would basically be perfectly spherically symmetric. Now, this is greatly expanded, so your ball wouldn't be oscillating quite as much, but I expanded it to give us an idea of what's really going on. So here, the drum is kind of analogous to this lowest mode, where the whole thing is expanding and the whole thing contracting, expanding, contracting, like that. Next mode would look something like this, where we now have, say, the top contracting while the bottom is expanding, and the bottom contracts when the top expands. Now, it's a little bit hard to see, but you just imagine right in between these two lines, there would be a nodal line right around the middle, the equator, you might say, of the sphere, where again, we don't have any motion. We've got contraction and expansion, expansion, contraction, but this line right around the middle, we have no motion at all. So our nodal line would be right around the equator. Now, this is say, the expansion in the vertical direction, or maybe the Z direction. We would have two others similar to this, but in perpendicular directions. Whoops, sorry, wrong one. So here we go, basically the same sort of oscillation, but now going left-right as opposed to up-down. Now we can definitely see this line right here is not moving at all. So there's our nodal line. If you could flip this around, that would be the equator right there. All the others are all moving except for that line. That's our nodal line for the oscillation. Then we've got another one, basically very similar to this, but moving front to back. There we go. So those are all essentially the same mode, kind of analogous to the square, where we had one like this and one like this. Basically the same mode, but rotated 90 degrees to each other. We can have other modes. Let's see, where was I? Here we go. Okay, so here we have the top and the bottom both contracting while the middle bulges out, but then the middle contracts when the top and the bottom bulge out. And these get more and more complicated. So here we go, something a little more asymmetric. And we'll look at one more. At this point, the resolution is starting to decrease, but I think you'll get the idea. There we go. So different parts bulging out, different parts going in. Now, if we could imagine looking again at the amplitude. So we're going to take these modes and come back to our amplitude here. If you'll remember, So that lowest mode, we might talk about the amplitude as being spherically symmetric. Rather than plus and minus, these diagrams actually use red and green. So the red means positive, plus green is in the opposite state. So the lowest mode would be spherically symmetric. The next one, where we have one side bulging out, the other side contracting, look like this. So here we have the one along the z-axis, bulging out at the top, contracting at the bottom, would be positive up here, negative here. Then we have one kind of front to back, positive, negative, and left, right, positive, negative, like that. So looking at it this way, we kind of see it's the same. Some of the higher modes then look like this, where we have different corners getting bigger. This one would be that peanut-shaped one, where the top and the bottom bulged out while the middle went in. So we have a positive lobe on the bottom, positive lobe on the top, with a negative ring around the middle. Likewise, we can have more and more complicated ones like this. This is actually one of the ones that we saw here. Well, anyone seen any shapes like this before? Say again? Balloons? And in particular, balloons. I know Paul knows. Yeah. What? Electron orbitals. Right. Well, this turns out to be exactly the shape as electron orbitals. When you look at the shape of electrons in atoms, they take exactly these shapes. Basically because when you look at the solution of the oscillation of a spherical drum head, the solutions turn out to be a mathematical function called spherical harmonics, which are exactly the same shapes that we get for the electron. Well, what does this mean? It means that electrons basically have these oscillating modes very much like the surface of a drum head, each with all of their own frequencies. So we can think of atoms as having these little electrons playing their own little tunes with their different frequencies, and each one of them is made up of trillions and trillions of atoms, all made up of these musical little electrons playing their little tunes all the time. You've got trillions and trillions of atoms undergoing chemical reactions millions and millions of times a second. Every time a chemical reaction takes place, the forces on these electrons change a little bit. And these frequencies have to change a tiny bit. Kind of like a little electron musician changing key millions and millions of times a second. So just sitting there, you're like a veritable orchestra with trillions and trillions of atoms with their electrons playing their little tune, changing key millions and millions of times a second. Sounds actually horrible when you think about it that way. I'm glad we don't have to hear it. But anyway, that's what the electrons are doing. Now, according to Einstein's theory of relativity, general relativity in particular, the most enigmatic objects in the universe, black holes, also seem to have their own little melodies that they play. When something falls into a black hole or hits a black hole or even flies by a black hole, the space-time, which is a four-dimensional combination of the space and time around the black hole, starts oscillating. Now, the space-time around the black hole is connected to the rest of the space-time in the universe. So, when the black hole starts oscillating, it sends out these gravitational waves through space-time into the rest of the universe. We've got something that kind of looks like this. This is actually a diagram of two coalescing black holes that are orbiting around each other and spiraling into each other, sending out these waves in the fabric of the universe, the gravitational space-time here, and these waves then propagate out through the rest of the universe. Just as an aside, I didn't really even think about this when I got this diagram, but Kip Thorne, who was at Caltech and worked on this, was actually, or is actually my academic grandfather, you might say. He was my thesis advisor's thesis advisor. Kip Thorne's thesis advisor was John Wheeler, and John Wheeler was the one that actually coined the term black hole. Physicists are now trying to figure out ways to hear the music from these black holes. There's one method called a Weather bar, which is a gigantic bar of aluminum that vibrates very, very slightly whenever one of these gravity waves passes by, and most of the ends they try to detect the motion of the ends of these weather bars. Another method, which seems to be much more reflectors between them so that light will shine, lasers from one to the other. As a gravity wave passes by, the distance between these will oscillate very, very slightly. By measuring the distance, or by measuring the change in the distance between them using laser interferometry, how two laser beams will interfere with each other, very, very small motions of the satellites can then be detected, and hopefully these gravity waves can then be associated with a particular black hole. Well, we started out with Johannes Kepler's ideas of music filling the universe. We looked down at the music created by electrons from the smallest things that we have ever measured, and we've ended up coming back out to the universe and seeing these gravitational waves that seem to spread out through the fabric of space-time itself. Well, with those ideas ringing in our ears, I would like to thank you for coming this afternoon. Any questions? Yes.
You were showing us the different figures where you have the warm line and the stationary. In life, in reality, what holds that line stable?
Good question. Nothing is holding it stable. Very much like the chain. If I can find an input. Okay. Oh, thanks. Okay. So just like a little one. Just like the chain, if we have one of these modes here, the middle is not being held stationary. It's just not moving because the other two sides are always pulling it in an opposite direction. So when one bulge is up, the other bulge is down. When the other one is down, up, the other one is down. So the chain is always pulling that point in an opposite direction. So that point just stays stationary. Now the multiple dimensional waves are doing exactly the same thing. So that when this side is up, this one is down, and so the line in the middle is being pulled up and down at the same amount, and so it stays where it is. And then as it comes the other way, it's being pulled the other way. So the node lines are always stationary because everything is pulling on in exactly opposite direction. Does that make sense? Okay. Actually, that brings up another point that I thought about mentioning. There are ways of playing different notes on an instrument called a harmonic. So that sometimes you might see a musician just basically touching a string very lightly, which damps out certain modes so that when that string is played, it sounds at a higher frequency. It's got these higher modes. And I'm not really trying to do this, but so for example, there we go. Okay. So I'm not pushing the string down, I'm just touching it very lightly. There we go.
On the banjo, that's called chime.
Right, right. Yes. So you can play chimes like on a banjo or harmonics on other instruments, and what you're doing is basically, let's say you've got this string and you touch it in the middle here. What's that going to do? Well, that's going to keep this mode from oscillating. It's also going to keep this mode from oscillating. So what you get then is basically this mode and other modes which have a node in the middle, and you only get those combinations of frequencies as opposed to the ones with the anti-node in the middle. So it's kind of another way of playing an instrument and getting a different sort of sound from it. Does that make sense? Okay. Any other questions? Well, that was 20 minutes for questions.
You said that they take wood off of the pieces, what they call it,
Yeah.
so they make it thinner in certain places, and that's until the tune stuff, that's what's known.
Right.
You know if that shape was originally experimented with or something?
I'm sure it was. I'm not exactly sure of the development of the shape of the violin. I know that there are other earlier instruments that are not in the same family. For example, the viola di gamba, which is viola di gamba, means leg, viola of the leg, which is played on the leg. So it was actually put on the leg and played like this. The top of that, one difference is that it comes up more like this, as opposed to being flat on the top. It comes up more like this onto the to the neck. Where's my neck? So it comes up more up the side here. So, but eventually the structure of the violin was chosen to be better sound than the viola da gamba, for example, and so that you only hear those in old groups that play antique instruments, or reproductions, I should say, also. I'm sorry, tell me again. Jim.
I teach English and poetry, and I'm here for that, because the use of that so often, poets and writers use that term just because it's weird.
Oh, yeah.
Especially in life, because we talk about the idea that we all are in the same, where we are properly, explained it in the sense of like the sphere that we all fit together. And also, you talk about sleep, cycle of time in harmony. And it says, we're using music metaphors so much. And it's found on that.
Yeah, now actually that term, the music of the sphere, that actually comes from prior to Kepler, from the Ptolemaic model of the cosmos, where Ptolemy thought of all of the, now Ptolemy's model was geocentric, so Ptolemy had the Earth in the center, and then he had these spheres on which the other planets moved, and then the outer sphere was the sphere of the stars. And then these were considered these nested crystalline spheres. And the outer sphere was called the prima mobile. That was the outer sphere that rotated and kind of dragged all the other spheres along with them. So, this structure where everything depended on each other and the motions were all related, that's where the idea of the music of the spheres came from.
Also, if I can add too, you said think of course context, and he had the idea of heaven to heal him for the music of the spheres. Yeah, and have one with God, and you reach that point of harmony.
Yeah, and the spheres didn't stop at the Earth, but kept going on down.
And he only had so many, he didn't have all the planets at that time. He had the moon, the sun, and the all this, and then we have the universe of God would be that.
Right. And I got this kind of wonderful analogy that I heard from a lecture with Richard Feynman, where originally, I love this idea. Originally, it was thought that the planets moved around the Earth because little angels pushed on the planets and pushed them around and kept the planets going around the Earth. But then Isaac Newton came along and said, no, what keeps the planets going around is this force of gravity, because they're actually being attracted to the sun. And so what Feynman said was, yeah, the angels are still there, except they're just 5 years later pushing on the force that I am supposed to do.
But I like the model just shows that it's pushing all around it, and really it becomes all of the universe.
Right.
One spot.
Right.
Follow. They don't teach it. We learn what it is. This is crazy. So let's go another way. One by rating, and the other one is not by rating. The possibility of God don't know, maybe one for another without any other one.
Yeah. Actually, Fred and I just Right. Fred and I just noticed a very interesting example of this morning. This morning. That's a situation called resonance. A resonance occurs when a system has a natural frequency at which it likes to operate. If you can have a forcing function that pushes on that thing at the right frequency, you can make that thing operate. An example that I always use in my class is pushing a child on a swing. And I have to tell you this terrible story. I was talking about resonance in my class, and I said, has anyone ever pushed a child in a swing in a playground? And I said, has anyone ever pushed a child? And this guy in the back put his hand up, and I said, in a swing, and he put his hand back down. So imagine you're pushing a child on a swing. How do you push them? How do you push them in the swing? Do you push them like this? Okay, no, probably not. Do you push them like this? No. How do you know? How quickly or with what frequency do you push them? They'll tell you, yes. How do you know? When they come back. You push them, they'll come back, you push them again. They'll come back, you push them again. In other words, you match your frequency, the frequency of your push, you would say the frequency of the forcing function, with the natural frequency of the piston. In other words, how rapidly does the child swing, right? So when you match your frequency to their frequency, you get the biggest response. In other words, the child has the biggest swing. That's exactly what's going on. When you have a system like a string, and you create a forcing function, which is the sound coming from the other string, that sound can push on that string and cause it to oscillate because you're forcing it with just the right frequency. Does that make sense? Now, the friend I noticed was that I had this setup just like this, and I was increasing the frequency slowly. I started out at a low frequency, and I started turning it up, and something on the table started vibrating. What's the vibration here? Oh yeah. And then as I turned it up, that stopped, and something else started vibrating. And I kept going, and then that stopped, and then something else on the table started vibrating. That's right. That's right. If you're going at a particular frequency, a particular speed, the engine is going at that frequency that'll cause different things to start rattling around.
Also, an opera singer can shatter glass. It's the same thing.
That's exactly right. If you get the frequency of the sound matching the natural frequency of the glass, exactly right. And this is so much more fun than all that can stuff.
Yeah, I was wondering, I think you forgot about some of the planets, right? You stopped hearing when they started Mars. Well, what about the other ones?
Well, good question. Actually, I stopped because I was sure that I wasn't going to have enough time. I didn't quite realize how fast I was talking. Now, this is kind of an interesting result. Now, Kepler only has data for 5 planets. Now, he would have considered the moon. Early on, the sun and the moon were also considered planets because planet comes from the Greek word planetes, which means the moon, or the wanderers, the wanderers. Because these were the objects that wandered through the background, the fixed background stars. The sun and the moon also wandered, so they were considered to be planets. But then by Kepler's time, he was really in favor of Copernicus's heliocentric model. So he really viewed the sun as being stationary, the moon as going around the Earth, but then the other planets, the 5 planets, orbiting the sun. And to Kepler, the 5 planets were Mercury, Venus, Earth, Mars, 6, Jupiter, and Saturn. So the 6 planets. The Earth being a planet, but not one of the 5 that we see in the night sky, which is the planet we always see when we're on. So Kepler believed that there were 6 planets. He did not know about Uranus, Neptune, and more Pluto. So that's kind of an interesting thing about this, because I believe that they actually do. Oh, now this is kind of interesting. Let me put this up here. This shows you perhaps a little bit that this is a little wave here. Right. So this actually includes. And this actually includes the 9 planets. So we've got obviously Kepler didn't have data for the outer planets, so this is kind of an extension. This is kind of an extension of Kepler's data to include the planets that we didn't even know about. I have a quality here. Yeah, I'll tell you. So, get more. You want more?
Yes, of course.
Oh, what more do you want?
No, I want to hear that.
Oh, you want to hear the plan? I didn't know there's so much of that before I start going to the crazy. I'll let you buy it.
But you say it.
Oh, all right. Yes, so we're sitting there going, what is that? I mean, I didn't know what it was. I thought it was stuff they were doing work on. So you can go. Oh, wait, I have to put on the light. Okay, so again, there's Mercury. You know what? I've tried to go through this and figure out each one. The outer planets I've tried to do this. As you can see here on all right, so there's unit. Here. Here it comes down. Mars. Yes. Oh yeah, oh that's right. Now I think Uranus actually is so low that it's more of a pulsation. That's here, I think that's here. You hear it? Here, that's it. I kind of like it. So the whole thing is. Yeah. Any other questions? do know that Chinese, traditional Chinese medicine is very much associated with horoscopes and astrology, that was the word. And definitely things like that. Yeah. And then you might be yeah. 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 Yeah, that's right.